This webcast continues the discussion of the lab for energy stored in a spring, and it begins at step 8. So we should have completed table 1. I know mine does not show all the values, but yours should have every row filled in. And then at step 8 it says let's make a graph of the applied force versus the displacement of the end of the spring. Okay, so we're going to need to put our data in Excel. And so you'll open up a new Excel file, and we're going to first build the table. The first column is the displacement of the end of the spring. That's measured in meters. And then there's the applied force, that the force that was applied to the end of the spring to either stretch it or compress it. That's measured in newtons. And then the elastic potential energy that was stored in the spring, and that's measured in joules. Notice that these titles are longer than the column is wide. If yours are going out beyond the width of the column, you can click this wrap text icon. Let's see, you're not seeing it. Let me get up here. You can click the wrap text icon, and that will make it wrap the way mine are looking here. Okay, so I'm going to type that information here in Excel. Okay, so I have all of my data now typed into Excel, and so then I'm going to make the graph that it's asking me in step 8. It's applied force versus displacement. And so to do that, here is the applied force, here is the displacement. And so I want to highlight the numbers for the first 2 columns, and I'm going to insert a scatter plot, just like we've always done. And we do need to put, of course, titles on our axes so that we know what this graph is. So this is the applied force versus the displacement of the end of the spring. And on the x-axis is the displacement. That was measured in meters. And on the vertical axis is the applied force, measured in newtons. I know this graph may look unusual to you. What's happened is that they have put the labels for the vertical axis next to the origin. See how the 0 on the x-axis is here in the middle? If you don't like this look, it is something you can change. You can click on one of these numbers for that vertical axis, do a right mouse click and say format the axis, and let's see, where it says labels, instead of saying next to the axis, you can say low, and that will move them over to the left. Okay, and so that just makes the graph maybe look a little bit nicer. Okay, so now that I have this graph, I want to put a picture of it in the lab report here under figure 1. Okay, so that was the graph that it's looking for there at step 8. And then it says, based on the shape of the graph, what kind of relationship exists between the force that is applied to stretch and compress the spring and the displacement? Okay, so the graph, let's see, let me make this blue. The graph of applied force versus displacement is linear, right? That is the shape of this graph. It's very nice and linear. Therefore, applied force is proportional to the displacement of the spring. Whenever you have a linear relationship, that means that one variable is proportional to the other. And so then it says give the value of the slope, including the units. Well, in this particular graph, because we're using a simulation tool, every one of these data points is exactly on the line. And so rather than doing linear regression, it's okay to just choose 2 points and calculate your slope from those 2 points. So, you know, I may choose the first and the last. And so I'll highlight those. And then I'm going to calculate my slope, right? So you want to show the details of this calculation. And so I have 400 minus negative 400. And this is from the second column where the units are in, let's go look at it again, are in newtons. And then, so that was my y2 minus y1. My x2 minus x1 is 1 minus negative 1. And that was in meters. And so I get something that is 400 plus 400 is 800 newtons divided by 2 meters. And so my slope is 400, 800 divided by 2, and the units are newtons per meter. Okay, and then it says explain the meaning of the slope. And so I'm going to explain it for every additional and I'm looking here at the what's in the denominator. For every additional 1 meter of the displacement of the end of the spring, okay, my first phrase is always explaining a 1 unit change of the dependent variable, and I want to name that variable. And remember, that's what I have on my x-axis here, displacement of the end of the spring. The unit is meters. Okay, so for every additional 1 meter of the displacement of the end of the spring, now I want to say, well, what's happening to this dependent variable, the thing on the y-axis? That's the applied force. The applied force, in this case it increased, right? Increases by 400 newtons. Okay. So I've explained how the dependent variable, the applied force, changed when there was a 1 unit change of the independent variable. Okay, so this slope is commonly called the spring force. Okay, oh, I'm sorry, no, the spring constant. Okay, and then it asks us to write a physics equation that explains this relationship. And it says we can ignore the y-intercept, okay, which is actually 0. So, you know, we're just going to put that in there. So here our independent variable, remember, is the displacement of the end of the spring. If you remember back to Unit 2, a common symbol for displacement is delta x, the change in position. Our dependent variable is the applied force, which we typically call uppercase F for force with a subscript of A for applied. And so I want to write the equation of that line. That's what the physics equation is. It's the equation of the line. Well, on the y-axis, right, I have applied force. So I'm going to have an equation that says applied force equals some slope multiplied by the displacement, right, because that's our x variable. Okay, so applied force equals our slope. I got a slope of 400 newtons per meter. Your slope will be different. And then my independent variable is the displacement. Okay. Let's go on to step 13. The applied force is a force applied by an external object, a person perhaps, to cause the deformation of the spring. So the applied force can be described as the applied force on the spring by the person. How would the spring force, that is the force that the spring is applying, compared to the applied force? Look at this. They are the same types of forces. They are both applied forces. They're both involving the same two objects interacting, the person and the spring. And so this looks very much like a situation where these are Newton's third law pairs. So the applied force that the person is exerting on the spring has the same amount of force that the spring will exert on the person, but they are in opposite directions. And so I'm going to put a negative sign there. So they, these two forces are equal in magnitude, but opposite in direction. They are Newton's third law pairs. So then it says, write a physics equation to explain the relationship between the spring force. This is not the applied force, but the spring force. Well, so the spring force, this is the force that the spring exerts when it is stretched or compressed. Well, it's going to have the same amount of force as the applied force, but in the opposite direction. So I'm going to put a negative sign there because I know it goes in the opposite direction. But otherwise, it's the same amount of force. So the slope will be the same, and the relationship is the same, right? So this equation is very similar to the equation for the applied force. The only difference is that now it has a negative sign. This one does not have a negative sign for the applied force. For the spring force, we do have a negative sign. Okay.